In this video, I will solve the problem that I assigned for my AP Physics students on a fluid-filled cylinder. So we're told that a fluid-filled cylinder has two openings, each with a movable piston. So I'll draw this cylinder in cross-section, and we've got these two pistons fitted into this cylinder. So I'll draw them like this. It's kind of a sloppy drawing, but you get the point. The large opening has a radius equal to 1 centimeter, so the radius over here is equal to 1 centimeter, and the small opening has a radius of 1/2 of a centimeter. So I'll call this radius 1 and radius 2. This is 1/2 of a centimeter as the radius, and this whole thing is filled with some fluid like this. And you're told that if the piston in the small end is moved in at 1 centimeter per second, so this moves with a velocity v1 to be 1 centimeter per second, and you're asked at what speed does the large piston move out. So we want to know the velocity right here, v2. Well, think about what's happening here. As this one's moving in 1 second, it's going to move, let's say, a certain distance. I'll draw the amount of fluid that it displaces in 1 second. It basically pushes this amount of fluid inward. And of course, that fluid has to appear somewhere, so it's going to basically push this piston outward, and whatever volume had been displaced by this piston is going to have to show up as volume displaced and on that side. So this volume right here, I'll call that volume 1, has to be equal to this volume over here, volume 2. Well, what's the volume here? It's going to be the cross-sectional area on side 1 times the distance it moved. I'll call that D1, and that has to be equal to the area of piston 2, area 2, times the distance that that one moves, okay, in 1 second. So what is the cross-sectional area of this? It's going to be pi times r1 squared, and the distance it moves is going to be d1, and here it's pi times r2 squared times distance d2. The pi's are going to cancel out, and so we can say the distance that this one moves is going to be the same as the distance this one moves, but scaled by a factor of r1 over r2 squared. And we know that r1 over r2 is 1/2 over 1, so it's going to be 1/2 squared times d1 is equal to d2. And coming up here, we'll say the distance that this piston moves right there, d2, then would be, let's say, 1 centimeter in a second times 1/2 squared, which is 1/4. So it's going to only move 1/4 of a centimeter in a second. So the velocity 2 is going to be 1/4 of a centimeter per second. So it's moving more slowly. Okay, and then we're told that the small piston is pushed with a force of 1 pound. So if there's a force being applied on this side, force 1, and force 1 we're told is 1 pound. We're asked with what force is exerted over here by this piston, F2. Well, we want to know what F2 is, how many pounds. Well, we can use Pascal's principle that F1 over area 1 is equal to F2 over area 2. So F2 is going to be equal to F1 times the ratio of A2 over A1, and F1 we're told was 1 pound. And so A2 over A1, well, that's going to be, well, I'll just do it slowly here. It's pi times radius 2 squared over pi times radius 1 squared. I'm assuming these are cylindrical shafts. So 1 pound right here, the pi's cancel out. R2 over R1 would be 1 centimeter over 1/2 of a centimeter. And you have to square both of those. So you get 1/4 in the denominator, so this is a factor of 4 times 1 pound, and so force 2 is equal to 4 pounds. So in other words, this is a force multiplying machine. You apply a small force, and this moves a fairly large distance of 1 centimeter in 1 second, and as a result, this right here can apply a large force, but it only moves a small distance. And remember the idea here, and this is the basis on which Pascal derived this, what came to be known as Pascal's principle right here. It was derived from the concept that the work that you put into this machine is equal to the work that you get out of this machine in the absence of any kind of frictional forces, internal drag in the system. But the force you put in is equal to the force you get out.